Hi there, welcome to the second video on modelling with logs, and this time we're going to have a look at this model. So again, just like before, we're going to start to make up some numbers that we could see in here. For example, you might think of y equals 2 lots of, say, 3 to the x, so a transformation on this graph, like a vertical stretch. You could make this base value here something like e, so we could have 2e to the x, something along those lines. And the reason you would expect and want to try and use this model over the other one is maybe if your graph looks something like this. If you imagine this continuing, we'd have that sort of look to it. Just put my y and the x there. So before we had that origin, and now we have a value here. It could be 1, and if it was 1, obviously a would be 1, but if it was another number, we'd start to look at our horizontal stretches. I mean vertical stretches, sorry. Okay, so just like before, we're going to take logs to both sides. So take log of y, log of a, b to the x. Just write log in front of both. Use our multiplication law. We're going to split these up. And you might be thinking, well, this looks exactly the same, but you'll see in a second that it's not. Using the power law, we'll bring it down, but this process is exactly the same. I'm just going to pop on another log y there. And again, we have a linear function. So if you think, wow, he's going fast, make sure you watch the previous video because that should make a lot more sense. Right, so we have a variable term because we know the variables are y and x. So every time I see a y and an x, that's my variable. And it means the a and the b's are a constant. So there's a constant and there's a constant. And you'll see this constant variable term here is now like swapped round. You wouldn't write it like this, would you? You wouldn't write x3 plus 4. You'd write 3x plus 4. So that's basically what's happened, b being a constant, so a numerical value. So I'm going to leave it like that because it looks confusing if you do it the other way. But let's have a think about what we're doing. So we've got a straight line, and this time our variables would be log of y, but this is where it changes. The variable is now just x. So like before, if we had a table of values from our initial experiment that gives us this sort of pattern, whatever these values are, I don't actually need to do anything with the x values because that in this model is my variable. I only need to find log of y. Okay, so I'd only be doing log of this value, log of this value, log of this one, log of this one. And again, I would get a straight line. So let's make that 2, let's make this 0.1 for example. I'm just making those numbers up because I haven't got any data here. So I know the constant on the constant variable is my gradient, so the constant term is log of b this time, and that's the gradient. And the constant term on its own, but that must be the y-intercept linking to graph knowledge that you're probably an expert at now. So log of a is the y-intercept. And you'll notice for both models, log of a was always the y-intercept. So therefore, we know the gradient is 0.1, so that's equal to log of b, and I have no idea why I wrote it that way round. And log of a we know to be 2. And if you want to, you can pop on the base values of 10 and we can work out what these are. So b is 10 to the power of 0.1 and a is 10 to the power of 2. So there you have it. So you've got y to finish off is equal to, so 100 times 10 to the 0.1 to the x, or you could tidy that up a little bit more, 100 times 10 to the 0.1x using your power law for indices. So if from our data we had something that looks like this, we could use this model and we would see if it fits using logs. And that's it. Best of luck.